statement. At the one off cycle itself, I can do what? Both the operation, addition and the subtraction operation. Did you understand? Are you clear this? The same clock we are doing the both operation, addition and subtraction. Now let us take very good example to illustrate what is the problem with the blocking statement and what is the problem with the non-blocking statement. So this is an example of ring counter. You know what is a ring counter, right? What is a ring counter? Where ones are traveling like what shape? How ones are traveling like? Shifting by what? Flip flop to the flip flop, bit by bit. So if I'm talking about 4-bit ring counter, 4-bit ring counter, how you can model this using the shift register? How many flip flops are required? 4 flip flops are required. 4 flip flops are required, correct? And then the clock, synchronous clock is feeding to all the flip flops. Output of this is feeding input to this, right? Output of this is feeding input to this. Output of this is feeding to input of this. Output of this last flip flop is feeding input to this, correct? Now, if you load the data like 1, 0, 0, 0, if I give the clock to this is the raising edge of the clock, the data will be shifted by what? Bit by bit to the right. Or you can do the left shift also. Clear. Now, the one clock, it will be 1, 0, 0, 0, initial clock. Next clock, what happens? 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. This is a ring counter operation. Now, let us see that if I am doing this using blocking model, what is the problem? How you can address this problem using a non-blocking models? How to write a behavioral model to this? How to write a behavioral model to this? You can see this is a ring counter. Module name is what? Ring counter. So what do we need? What are the inputs is? Clock. And first we need to initialize the data. If you keep all zeros, if I'm keeping, instead of if I'm not going to initialize any value, if I'm keeping all flip-flops to 0, whether I can encounter with the ring counter operation here? No, zeros only, it is just rotating. Correct. Now I should at least keep one flip-flop to 1 and then I should rotate. Then that behaves as a ring counter operation. Now first I'm using for input to initialize. I'm going to use what? Initialize is the one input. Then count is the output. Count is the output. Then the clock. Now what are the inputs are here? Clock is the input. Initial is the input. Then always rest. So what counter we are designing ring counter? 8-bit ring counter. 7 down to 0 means it is 8-bit ring counter. Now always at the what? I'm using at positive edge of the clock. So we are writing begin using conditional statements. If my initial is equal to 1, if initial is equal to 1, what we are doing? We are loading the count. Count we are loading into what? 8-bit means what? I'm loading like this. I'm loading count to what? Now count. This is my count. How many bits counter we are designing ring counter? 8-bit ring counter. 8-bit ring counter. So this is a count. So we are loading what? 1, 0, 0, 0. Here this is 0, 0, 0, 0. We are loading the data is when initial is equal to what? When initial is equal to 1, we are loading the data. 1, 0, 0, 0. So what I'm doing? If this is initial is equal to 0, where I'm going? Else body. In the else, what we are doing? Count is equal to what operator this is? Shifting operator. Left shift operator. So what statements I'm using here? Blocking statements. If I use the blocking statements to model the ring counter, whether I'll be getting a correct output? Now can you understand the execution of this program though? If initialization is equal to 1, it will load this. If this is equal to 0, where it is coming? Count is equal to, I'm shifting. This is nothing but a shifting operation, right? Ring counter means what you can see. I'm doing a right shift operation. Correct? You can also do the left shift operation, right? This is also fine. Correct? This is also ring counter operation itself. Are you clear? Now what I'm doing in this case is count is equal to what? Blocking models I'm using. Count is less than 1 means what operator it is. This is nothing but a left shift operator. Left shift operator. How this will be scheduled? How this will be scheduled? How this will be executed? This is a blocking model, right? Sequentially, first this will be executed. Then this will be executed. First, if this executed, what happens here? Left shift by how much? 1. What we are loading to the counter is? We are loading the counter is what? 1 0 0 0. 1 followed by 7 zeros. If you shift this count by what? 1. What happens here? This is 0 0 0 0 0 0 0. Is it 1? We are not doing the arithmetic shift. Arithmetic shift means 3 less than symbol. Now by default this will be filled with what? Zeros. Left shift and right shift operation. Suppose if I'm using A is equal to 1 0 0 0. If I shift A by bit one side right, what is the A value is now? 0 1 0 0. It will divide the number by power of what? 2 power 1. Correct. If I'm shifting this by 2, what happens? A shifted by 0 0 1 0. Same thing I'm doing. This is shifted towards the left. Now this bit is shifted here, correct? This is shifted here, this will shift 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 here. This will be what? 0. Now what is my count? Now it becomes 0 0 0. Correct? Now after this, you can see what I'm doing. Count of 0 means what? Count of 0 means first LSB value. First LSB value we are assigning to what? Count of 7. This is nothing but your count of 0. This is a count of what? Count of 0. This is nothing but what? Count of 7. Now what I am doing? Count of 0 is equal to what? Count of 7. Count of 7. Now what is count of 7 is nothing but 0. Now if I get this is 0 here, whether I will get the model of the ring counter operation? No. What I mean to say in this example, you should understand that how these blocking models will not give us the correct result. Did you understand? What program I am doing here? Ring counter operation. Counter operation. First, I am designing the 8-bit ring counter. I am initializing the counter with what? Count with 1 followed by 7 zeros. If my initial is equal to 1. If initial is equal to 0, then I am doing what? Shift operation. So I am using, when initial is equal to 0, it goes to the else bar here. Count is equal to what? Count is less than 1 means I am shifting left by what? 1. How this will be executed, this sequential, this is nothing but blocking assignments. First this executed. This executed means what is my count is nothing but none. I am shifting this by how much? By 1 means now count becomes all 8 zeros. Now after this what happens here? I am assigning count of 0 is equal to what? Count of 7. The count of 7 value is equal to 0. Whether I will be getting the ring counter operation here, if I am using here the blocking statements, is it correct? The solution is correct? No, right? So how the ring counter will work for this one? If this is my 1 0 0 0 again 0 0 0 0, what is ring counter operation is? It should get like 0 0 0 underscore 0 0 1. Next clock it should be what? 0 0 0 0 0 1 0. These are ring counter operation. Again this is what? 0 0 0 0 1 0 0. But what happens in this case? If I go with the blocking statements, I am sure this is count is initialized here. Count is set by how much? 1. Now this is my count. After this, if I am using count of 0 is equal to count of 7. So I will be getting again what? My count is equal to all are 0 0 0 0 0 0 0. whether I'll get a correct solution to if I'm using the blocking models for the ring operation, ring counter operation. Is it clear? This is how, when you're doing the modeling of any design, we should see the proper way of writing the blocking statement and non-blocking statements. Here, if I'm using to model the ring counter using blocking statement, I'll be not getting the correct output. Is it true? Look at this example. Now, this solution is wrong. Count of 7 will get the O written in the first statement. The rotation of bits will not happen. Right? This is what I'm writing. The rotation of bits will not happen here. If I'm assigning count of 7 to count of 0, I'll be getting the count is nothing but 1, 0. Rotation of bits will not happening here. Clear? Then what is the solution to this? Now we can tell me what is the solution to this. I'm not getting a ring counter operation here. Okay, what is the solution to this? Using the non-blocking operation. Now understand, I'm changing this blocking statement to what statement? Let us make this into a non-blocking statement. All these non-blocking statements are scheduled here. These both are executed concurrently. Correct. Now this count becomes what? Initially count is nothing but 1 followed by 8 zeros. Now this is also executed at same time, this is also executed at same time. But when this is executing, this will take this count value that is shifted. And again, this count of 0 will get what one? This count value or this count value? Initial count value. So if I'm taking the initial count value, what is the count of 7 is? 1. Now 1 will be assigned to the count of 0. Is it? Use the non-blocking operation. So if I'm going with this example with the blocking, I'm not seeing the effect of what? Rotation of the bits. It will give the wrong solution, wrong output. Correct. The same thing if I'm making this into what? Non-blocking, I can see the effect of what? Ring counter operation. This is example is clear? Are you clear this one? Now suppose I want to do ring counter operation using blocking only. How to do? Did you understand my question? If I go with this example, non-blocking will not use the correct result. Wrong answer. There is no shifting of bits will happen. I should do using temporary variables. Using 1 by 2 is nothing but what? Temporary variables. Huh? You can think, is any other way you can do this? Is any other way you can do using blocking statement itself? Is any other way? You can see this program. This is nothing but what I'm doing. Non-blocking, right? The one I have explained for the non-blocking. Now this is the correct version of the code. Correct? What happens first? These two are concurrently executed. Non-blocking assignments. Correct? And then this count will get this. Again, this count of 0 will get this count. This 7 value will be assigning to what? Count of 0. Then you can see that since non-blocking assignments are used, rotation will take place correctly in this code. I'm changing the blocking statement into what? Non-blocking statements. So my question is that I want to do the ring operation, ring counter operation using blocking itself. How to do this? Using one way, you said that use the temporary variables. Assigning the value to the temporary variables, then you can sequentially use equal to 1 and loading the data. Okay. Then what I'm doing, count is equal to what I'm doing here. What operation this is completely? What operation this is completely? I'm using here concatenation operation. What operator I'm using here? Blocking operator. Count is equal to, correct, count is equal to So what I'm doing here, in this case, count 6 down to 0 means what? Up to here, correct? This is a count of 0, count of 1, 2, 3, 4, correct? Again, what happens here? Count of 7. Count of 7 is assigning to the count. Count of 0. So that by going, this is the correct way of modeling using what? Blocking statements. You can use a concatenation operator. Another way is nothing but you can go with the temporary variables, assign the value, then you write a sequential execution so that you can model the what? Ring counter operation. Is this is clear? Now what happens in these cases? What happens? This count becomes what? Now I'm concatenating. Count 6 down to 0 means what? This is a 1. Correct? 6 down to 0. Count up 7 means what? 1. Now how we are assigning to this count is? How we are assigning to this count is? How this concatenation will happen?
0, 0, 0.
Count will get what now it is. Now this is assigning to the LSB, right? Count of 7. What is count of 7 is? 1. Now this becomes 1. Then all becomes what? 0, 0, 0. Let us write underscore 0, 0, 0. Correct? This is one way to addressing blocking statement to do the correct way of ring count. This is clear? These two examples are clear. Using non-blocking, using blocking itself, how to do. The very first one what we have done here is, so this blocking statement will not give the correct solution. So there is no rotation of the bits will happen in this program. Did you agree? Yes or no? Yes, right? Now this same thing you can do using what? Blocking. And this is using what? Blocking itself by using the concatenation. Now I am getting this count of LSB bit is 1. Now I am going to shift to this one. Correct. Now you can shift this so that rotation of bits will be happen. Are you clear? This we have done. Blocking itself, you are doing the what? Rotation operation. So this is what exactly it is required. When to use the blocking, when to use the non-blocking statement, when you are a good designer for the behavior modeling technique. Is it clear? Now let us go with the mixed mode of blocking. Basically, that is not recommended to do the mixed mode of blocking. Means same always block. We're not allowed to write one blocking models and non-blocking. So if you talk about the blocking versus non-blocking assignment, so we shall now illustrate some examples how the modeling styles is to the simulator or synthesizer to capture the behavior of the model circuit. Now you have a blocking circuit and non-blocking circuit. How this will be modeling influences to the synthesizer to model hard way. Writing the blocking and you write the design file. This is hard way. We'll see that blocks. So it is a very important record to what we need to do. So it is recommended that if you are getting any confusion, write a Verilog code, simulate it, analyze the output. Like the way we have done it, what? Ring counter. If you do that blocking assignment, there is no simple will happen. rotation of bits will be not happens. Now by changing that into what? So that you see the effect of getting shifting up. Is it clear? Now we are non-blocking. How this will be synthesized? Or it is converted. Example. Okay. Let us take an example here. You can see what is the example one here is. This is nothing but what? Blocking. This is nothing but what? What is the operator we are using for blocking is less than or equal to is block. Tau both will give this of C. How it will be the C value will get the value of original value of B. So the value of C for what time? 10 time units after the begin end block starts. Once this begin end block starts, the C will get at what time? 10 time. What value? B value. At first T is equal to 5, B is assigning to the A. Correct. This is blocking statement. How this blocking statement should be executed? First this will execute, then it comes here. This value of this will be assigning to what? C. So here the value of B will be assigned to the C 10 time units after the what? Begin and end the block will start C. Correct. This value will be assigning. B will be assigning to C after what time? 10 time. Now coming to this non-blocking. How this non-blocking will be executed? So here A is scheduled to get the value of what time? 5 time. And then B 5 units into the future. Correct, means A will also get the scheduling time of 5. C is also at what? 5. But B is time units to the future, means this value is assigning to the A, the 5 are concurrently executed. So C is also scheduled to get the value of the 5 unit into the further. Did you understand? Now here the values of if both the programs, the values of C will be different. Correct? In this program, what is the value of the C is? A after 10 time units. Means C is not C is assigning to what? The value of B. Whatever the value of B will be assigning to what? C. What about this non-blocking statement? The value of C will be different for these two cases, right? What is the value of C is? Initially, what is the value of A that will be assigning to what? C. Because these two are scheduled like what? Concurrent execution. Non-blocking statement. So this is one example. If you use this, both are same. A is equal to B, C is equal to A. Here also A is equal to B, C is equal to A. But these are blocking statement. These are what? Non-blocking statement. The C will get different values of these two cases. In the first case, C gets the what? The value of B. Whatever the value of B. Here C gets the values of what? Value of initial value of A. Initial value of the A. Now, so that these two different cases will work, gives the result, different result. Did you understand now? This is one example. Now let us go to the next example. So when the example is how synthesizer will understand when you write the blocking model and non-blocking model. Correct. We are writing a model for the, you can see always at the positive edge of the clock. We are doing begin. Q1 is assigning to what? Input A, and Q2 is assigning to what? Q1. So Q1 gets the value of what? This is a Q1. How your synthesizer will do, see this program are converting to as a hardware. This Q1 is getting the value of what? A. Then what is the Q2? Q2 is getting the value of what? A itself, right? First this will be executed. Then what? This will be executed. What is the Q2 is getting the value of what? A itself. Because these are what models? Blocking models. this will be executed and then this will be executed. Therefore, Q2 get A only. I can write what is a Q2 is nothing but A. The synthesizer will models this program as what? Two parallel flip-flops. Correct? Did you understand? This is actually we are doing what? Shift register operation. This is output of input is connecting into Q1. Correct? Again, the output of this Q1 is connecting into what? Q2. Q1 is connecting into what? Q2. D flip-flop. So D flip-flop means output follows the input, right? So when I'm going with these blocking models, the first flip-flop Q1 gets the A, and blocking models Q2 also get A itself. This is how it is going to see. This program will be seeing like this one. Synthesis 2. Did you understand? Say for example, I change this into what? Non-blocking. Non-blocking model. Now how it is going to see this as? Q1 gets off at initial value of A. Q2 gets the initial value for Q1. Correct? Now this will be modeled like this, you can see. This is your non-blocking model. This is a blocking model. It is modeling like what? Parallel flip-flops, two flip-flops. Now you can see I'm changing this into what? Non-blocking model, where Q1 gets the what? Initial value of A, and Q2 gets what? Initial value of A. This is some sort of shifting operation. Correct? So this Q2, this initial value getting what? Q2. Now this is modeled as a what? Shift register. If I'm removing this non-blocking model to the blocking model, how this is modeled as? Or that will be modeled as two parallel flip-flops. Not as in, what is shift register means? The data should be shifting towards the right. Correct? Here in this case, it is shifting the right. If I give A is equal to 0, okay, initially this both flip-flops are 0, 0. If I give the clock, what happens? Now A is 0 means this should get 0. This Q1 initial value will going to what? Q2. Correct. If I give A is equal to 1, give the clock, what happens? Now Q1 gets 1. The initial value of this Q should get shifted to here. 0. The next clock, what happens if I'm giving Q A is equal to 1? What happens here? Q1 is equal to 1. And initial value of the Q1 will be what? This 1 will be shifted to here. This is nothing but a shift register operation. Is it clear? If I do the shift register operation with what? Blocking, that will be modeled like this. Parallel flip-flops. Not like in what? Shift register. If I'm using this as a what? Non-blocking statement, this will be modeled as a what? Shift register operation. Now I think this example also clear. When to use blocking and when to use non-blocking. Now let us take few more examples. So this is example 4. Now this is a non-blocking I'm using. Two always blocks I'm using. The two always blocks, Q2 is equal to what? Q1. Earlier what we done, Q2 is equal to Q1. First in the non-blocking, Q1 is equal to A, Q2 is equal to what? Q1. In the first always block I'm writing what? Q2, non-blocking of what? Q1. Again, this is always at the positive edge of the clock. Q1 is nothing but what? A. This is also modeled as a shift register itself. Because both these statements are executed how? Concurrently. At time t is equal to 0, this Q2 will take the initial value of what? Q1. And this Q1 will take the initial value of what? A. This is also modeled like a shift register. Are you clear? Did you understand this? If it execute this or this first, whichever executing this, because this both the parallel procedural blocks are started time t is equal to 0. Which one will start first? That is depending upon the simulator dependency. Maybe it start first followed by this, or this starts first followed by this. If you start either of this, now I'm using the non-blocking technique here. Now Q2 get the initial value of what? Q1. So Q1 also get the initial value of what? A. So that this will be model like what? Shift register operation. Is it clear? Now can you tell me what is this will do? What this will do? What statements I'm using? Blocking statements. Correct. Blocking statements. This is also executing at what? A is equal to 0. This is also executing at what? A is equal to 0. Correct. How this will be scheduled and executed? Q1 will get the initial value of A. Then Q2 will get what? The present value of A. Q1 means Q2 is assigning what? A itself. Now here it is nothing but somewhat non-deterministic output, indeterminate output. So this Q1 gets the value of A, but to do the shift register operation, Q2 should follow the what? The previous value of Q1. But here what happens? Q2 is getting what? It is getting what? Indeterminate. Correct. Initial value of the A. Q2 will be getting the indeterminate value. Is it clear? By changing this into the non-blocking model, this is will be modeled as a what? Shift register. Q2 will get the initial value of Q1. Q1 will get the initial value of what? A. Are you understanding? Is it clear? This is nothing but what? Blocking or non-blocking? Blocking. So non-blocking will use the modeling as what? Shift register. This is the one. Same thing if I'm removing this less than operator here, that becomes what? Blocking operator. This blocking operator will give what? Indeterminate. Q will be what? Indeterminate. Did you understand this blocking and non-blocking? Now let us go one more example. So let us see this example. So we are modeling for what? Shift register, 4-bit shift register. What is 4-bit shift register? How many flip-flops are required? 4 flip-flops are required. Correct. So here clock is the input. Clear, one more clear is the one input. A is the input. A is the output. So if I write the shift register, this is how you can model the shift register, right? How many flip-flops? 4-bit shift register means this is the one. Correct. And then this is connecting into the clock. This is connecting into the clock. Shift register means what? CISO. Each flip-flop output is feeding input to the next flip-flop. Correct. This is the output. This input is A. Output is talking about B. And then all these intermediate wires are connecting as A, B, C. You can see, and then also this is connecting into the clear pins. So octilo clear pin. So this is a clock. This is a clock, and this is nothing but clear. This is what? The 4-bit shift register, 4 flip-flops. Input is A. Correct. Clock and clear are the input. A is the input. E is the output. Output reg E. And then we are taking reg B, C, D. Intermediate. This we are considering as a reg B, C, D. Outputs. These are output is B, C, D. Intermediate registers output. Then always at the positive edge of the clock are negative clear. Negative edge of the clear. Means what? What is this? Is nothing but. This is nothing but negative edge of the clear means clear will be 0. When clear is equal to 0. If clear is not is equal to 0, what happens? There is no shifting operation. Shifting operation will take place only when clear is equal to 0. I am using if not of clear. Not of clear means what? It is octilo clear. Octilo clear means when it is 0, it has to do shifting operation. If it is not of clear means what? 1. If clear is equal to 1, what we are doing? All flip-flops B is equal to 0, C is equal to 0, D is equal to 0, E is equal to 0. Then if clear is equal to 0, where it is going? Else body. The else body, we are assigning what? E is equal to D, D is equal to C, C is equal to B, B is equal to A, then N, then we are in the module, end the initial begin, end the always, then end the module. Now this will be correct circuit for modeling the shift register. What statements we are using here? What statement is that? Blocking statement. This is modeling as a 4-bit shift register. How the 4-bit shift register will works? Suppose this is my data, correct? If I shift this by right side, what is the data it should be? 0, 1, 0. Correct. Again, this is nothing but what? 1, 0. This is nothing but what? 1. Let me write these are what? X, 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 X. The last one is 0. This is 0. Correct. This is nothing but a shift register operation. 4-bit shift register operation. What happens here? What I am writing? E is equal to what? D. Then what? D, this is nothing but D is equal to what? C. Then B is equal to what? B is equal to, C is equal to B. B is equal to A. Correct. This is what I am using. To model this, I am using this one. E is equal to what? D. D is equal to C. C is equal to B. B is equal to what? A. Did you understand? This is what model we are doing. Now E will get the value of what? D. So once it start executing, this is blocking models. First this will be scheduled, right? E is equal to D. Now E gets the value of what? D. Again it goes here. What is D value is? C. D value will get what? C. Again what is C is? B value. Again what is B value is? A. If I write like this is the correct way of modeling the 4-bit shift register using blocking statements. Correct? Did you understand this? Now here I am getting E is equal to D means shift register operation means what? E will get D. D gets value C. C. This is first, this will be executed. Correct. E value gets what is the value of D. Again D value gets what? C value. What is C value gets? B value. What is the B value gets? A value. Correct. Now this is a correct way of I am representing using what? Blocking model. Blocking model to what? Using how many shift register? 4-bit shift register. Now what happens if I am changing the order? I'll change the order. I'll reverse the order then. I reverse the order means what? B is equal to A, C is equal to B, D is equal to C, then E is equal to D. Now I reverse the order here. Now whether this will be modeling as a 4-bit shift register now? Huh? You understand this? What is the B value will get? A. Again C value gets what? B. And then D value gets what? C. Again E value gets what? D. Is correct way of modeling? Yes, this is a correct way. Yeah, shifting in another direction. Whether this is modeling as a shift register? Is it yes? Yes, this is correct. Okay, before that, you tell me, did you understand this? How this will be modeling using blocking model? How you can model the 4-bit shift register? If I write E is equal to D, D is equal to C, C is equal to B, B is equal to A, this circuit will synthesize tool generate correctly like this. This is a shift register. What I am writing in the easy notepad, correct? E follows what? D. D follows what? C. C follows what? B. Again B follows what? A. This is a clock and this is active low clear. Did you understand? Now this program, in this program I am using the blocking model, blocking statements. This will synthesize correctly as a what? Shift register. Correct. Now let us take this example. This example, what I am doing in this case is, you can see other part of this program is the same. What I am doing here, we just reverse the order of what? These procedural assignments. These assignments are writing using what? Blocking assignments. We have reversed the circuit. So we have reversed the what? Order. We have reversed the order. Now whether this is working as a 4-bit shift register, 4-bit shift register, what is B value will get? A. Let us take A is equal to X. What is the B value is getting? X. Then what is the C value is getting? What is the B value now? It is sequential execution, right? B will get X. What is C will get? X itself. What is the D value will get? X itself. What is the E value will get? X itself. Are you understanding? Now what happens in this case is E is following the A. So this will be modeled like E is equal to E. It is not going to synthesize like a 4-bit shift register. If I am reversing the order for the blocking statements, this will be modeling as a like this. This is modeling like this. Now it is a 4-bit shift register. Now because A is following what? E. Correct. A is following E. This will be synthesizer will be modeling like this. A is equal to E. This is not a correct way of synthesizing to what? 4-bit shift register. Are you understand? The way I am writing the order here, this is correctly modeling as shift register. Shift register means what? Last flip-flop output following the previous. That is following the previous one. That is following the previous one. Correct. The way if I am reversing this order, this will be modeling like this. You don't understand? Now, let us take an example, same example with the non-blocking statements. Non-blocking statements. If I am taking this as a non-blocking statement, what happens here? What happens here? All these non-blocking statements are what? Concurrently executing. E gets the value of what? Initial value of D. And the D will get what? Initial value of C. And C gets the value of what? Initial value of the B. And B gets the what? Initial value of the A. So that D gets E gets D, D gets C, and then C gets B, B gets A. Correct? This is a 1. This is a 1. I am using what? Same program. What I am using here? Non-blocking statements. Now this will be synthesized. First, all these right hand side of expressions are evaluated in parallelly. Correct? So that order of statement is not important here. If I reverse this order also, it will be modeling as what? Shift register itself. If I am writing this like what? B is less than or equal to A, C is less than or equal to B, D is less than or equal to C, E is less than or equal to D. This is fine in this case if I reverse the order also. All these are what? How it is executed concurrently. B will get what? Initial value of the A. C will get the initial value of B. And D will get the initial value of the C. E will get the initial value of the D. So that there is no problem if I am changing the order for the non-blocking statements. This will be modeled as what? Shift register. This will be modeling like this shift register. If you changing the order of this, the way we are writing the statement, procedural statement, if you change the order also, not effective to do the modeling of the shift register. But the same thing what happened when I'm using blocking models. If I change the order, if you change the order, so I have changed the order here. This will be modeled like what? E following the A flip-flop. Only one flip-flop it is as a modeling this. You don't understand? So what is a good practice now? What is a good practice? Practice is whenever you are dealing with always at the edges where a positive edge or a negative edge or synchronization. Whenever you do synchronization, used to practice with what blocking models? Non-blocking. What the procedural statement is? Non-blocking procedural statements. So that's why it is recommended you to use the blocking for what? Combinational. This is one example you can see. 2-3 examples I was talking about today. How that non-blocking will gives the correct. So one example is where ring counter. So one example is modeling the shift register. The way if I'm changing the order, it will models as a different circuit. Is it clear? So that whenever you see at the positive edge of the clock, negative edge of clock, synchronization with the clock, always you should better prefer to what procedural statement is, non-blocking procedural statements. Is it clear? So this is how you can use the blocking and non-blocking statements. So in this example, the way we change the order, the first one is correct activity, but it is modeling as a shift register. The way we are writing the procedural statements. If I reverse that order, that is modeling as a single flip-flop, where E following the A flip-flop. Recommended cell for the for modeling for the circuit statement can be appearing in any order. Chances of error is less if I'm going with what model. Please. If I change the order also, so this program is modeling like a what is this is nothing but 4-bit shift register with up to low here. Did you understand? Now you at least you got the point that when to use the blocking, when to use the non-blocking statements. What is the use of the blocking and non-blocking statements? Okay, any good practice? Getting confusion, what do you need to do? If you're getting confusion that when to use the blocking and when to use the non-blocking, you write a program, simulate, see the output. Then you can decide that I should use the blocking statement or non-blocking. Good practice. It's a good practice. So I have done 3 or 4 examples with the blocking and non-blocking differences. What will happen if I use this blocking to model this? What is the result I am getting? In any time you are writing using blocking and non-blocking model in the behavioral style, you are getting confusion, you can model the blocking and non-blocking and check the outputs. See the results. Is it clear? So it is recommending that what you should do. Sequential circuits, correct? So recommended style for modeling the what? Sequential circuit using what? Non-blocking module. For combinational logic circuit, go to the blocking. Now let us see that whether I can go with the what? Mixed blocking models. What do you mean by mixed blocking models? Combining of both the blocking and the non-blocking. We are highly not recommended to go with this. Not recommended to go with what model? In the same procedural statements, in the always block, don't go with what? Don't go with mixed means blocking and non-blocking. This is not recommended. Occasionally, sometimes you are going to see this kind of mixed modeling style. Okay. So mixed blocking and non-blocking assignment in the procedural block will not be recommended to do the program. Okay. Now let us see a few examples on this. Okay. So it is possible to combine both the blocking and non-blocking assignments in a same procedural block. Like a what? Always block. Simulator or synthesis tools support this type of usage also. Whatever the synthesis tool you are using, if you are writing in the same always block, if you are using what? Blocking and non-blocking, it will support. But, however, interpretation of the circuit behavior under the such mixed usage is not very straightforward. If you are modeling with the what? Mixed blocking and non-blocking. So the interpretation of the circuit behavior, you can't interpret the behavior of the circuit under such mixed usage is not very straightforward. So not recommended for what? Designers go with what modeling? Mixed blocking and non-blocking. So we'll explain few examples for this mixed blocking model. So such mixed should be avoided in the what? Design. You can use, if there are multiple always blocks are there, in one always block or a procedural block, you can use what? Blocking. In another always block, you can use non-blocking. That is a good practice. But it is recommending that in the same always block, don't go with what? Blocking and non. But your synthesis tool or simulators will understand and producing the output. But interpretation of behavior of the circuit is not straightforward in this case. So that we should avoid what? Mixed blocking, mixed mode of assignment will be not straightforward. Okay, let us take few examples of this. You can see what is this is. This is example one. You can see always at the rate. So always at the rate star, you know what is the meaning of star rate? Any value, multiple values, correct? Begin what we are doing. X is equal to 10, X is equal to 20, Y is equal to X. Then we are giving a time star. Correct. So what is the value of Y will get in this? Y is equal to 20. What models we are writing here? Blocking models. So this yields a result of Y is equal to what? X is equal to 20. Y is also what? 20. Only what this model is. Using only one assignment, procedural assignment is what? Blocking assignments. Now coming to the second example. So in the same always procedural block, procedural statement, we are writing what? Mixed. So we are writing X is equal to 10. Then X is equal to 20. Y is what? Less than or equal to means what? Non-blocking model. Y is equal to X. Now in this case, what is the X and Y value will get? How this will be scheduled and executed here? Now these two are executing at the same time, right? X is equal to 10. Again X is equal to 20. Y is what? Non-blocking statement. So Y will get the value of what? X. Initial value of the X. Therefore what? X is equal to 20. Y is equal to 20 in this case. Both gives the same result. This alone blocking assignment will give the same result. If I go with mixed model also what? Same result. But what I said, the interpretation of behavior of the circuit is not straightforward here. Correct? So I am not properly, it is not straightforward to interpretation of the result X and Y value. If I go with what? Mixed modeling. So the same result will shown in both the version of the code. Correct? This also gives X is equal to 20, Y is equal to 20. Here also it gets X is equal to 20, Y is equal to 20. So X will be assigned the 10 and then 20 in first case. Both the time at what? These are time what? T is equal to 0. Here also what? T is equal to 0. Correct? The value of X at the time T0 will be assigned to the what? Y. Here also Y also is getting at what? Time T is equal to 0. But Y will get the value of what? Here 20. Here also X is what? Now it is 20. These are concurrently executing. Then Y gets the value of X is 20. So both are same. Both will give the same result. But interpretation of the result will be what? Not straightforward when we go with the mixed blocking models. Are you understand? This one example. Is it clear this? Now let us go to the next example. Can you understand this example? This is an example of what? Blocking. So blocking model. So X gets value of 10. Then Y gets the value of what? 10. Then X gets value of what? 20. Now what is the Y value is? Y is equal to 10. X is equal to 20. Blocking. Blocking statement this is correct. Now coming to this. This is an example of what? Mixed. Blocking and non-blocking. Then what is the output of this? First X is equal to 10. Correct. Again, these two are, first this will be executed. at time t is equal to 0. This also is executed at time t is equal to 0. But x gets a value of what? X gets a value of 20. Now what is the value of y is? Now y will get the value of 10. So the interpretation of x and y values is not straightforward in this case. If I go with the mixed model, the same result will be shown in both the versions. Here y will be assigned to what? 0 at time t is equal to 0. The final value of x will be assigning to what? 20. X value gets the 20. You understand? So always this is not recommended. I say that result will be not a straightforward for interpretation of the results. Okay. So that's why I'm not going to talk much about what mixed mode modeling thing. So we'll be going with the blocking and non-blocking assessments. I hope this is clear about regarding blocking and non-blocking. So with this, we'll stop the blocking and non-blocking. In the next session, we'll be starting with the timing controls. What are the timing controls for the behavioral model structure? Okay. What are the types of timing controls are there? What are their usages in the behavioral model? We'll see that in the next session. Okay. Today, I am advising you to take up these examples. You write a program, write a test bench to this, then understand how it is behaving for the modeling blocking models and the non-blocking models. Is it clear? I illustrated 2 or 3 examples here. You write a test bench and see the result of both blocking and the non-blocking. Is it clear? So with this, I will be stopping the session here today. The next session will go with timing controls. So as of now, in the behavioral model, we talked about procedural statements. What are the procedural statements are? Blocking and, initial and always flag. And then we talked about the statements we can use initial, the procedural statements are blocking statements and non-blocking statement. We saw that what are the advantages of blocking and non-blocking. So we have more advantages in the non-blocking. Only problem with the non-blocking is what? What is the problem with the non-blocking is? Huh? Can you differentiate the blocking and non-blocking?
Extra register.
Can you differentiate the blocking and non-blocking? Blocking and non-blocking. How this will be executed? Sequentially. This is nothing but what? Concurrent execution. This is a concurrent execution. This is nothing but sequential execution. This is recommended to do what? Combinations.
Combinations.
This is nothing but recommended to sequential. Sequential circuit. What is another advantage? There is a race problem, right? Race conditioning there. When you get this race problem, sampling variables. Correct? Here, it avoids the what? Race condition. Next is what? There are 2 operations in the non-blocking, right? Read operation and correct. Read operation and write operation. Read operation and write operation. So here it is not working like what? Read operation and write operation. No. Read operation and write operation. Correct? And it will not create any temporary variables internally in the simulator. Correct? It is not create any temporary variables. Correct? What about the non-blocking? Internally, correct? Internally, it creates a what? Temporary variables. Temporary variables. Next. Because of this, it is internally creating the external means temporary variables, it need a extra memory. So that will burden the simulator. Correct? So non-blocking will what? It burdens the what? Burdens the simulator. Burdens the simulator. What about this? There is no like read and write operations here. So it will not burden the what? Simulator. It will not burden the simulator. Need to understand. So this is the differences between what? Blocking and non-blocking
Hello?
assignment. Yeah, hello.
Hello, sir. Sir, the blocking assignment, sir, you can use in a sequential also, right?
Yeah, you can use the blocking also, you can use the sequential. I
But
said
you
one
are saying-
example, right? I
Yeah,
say
but
it
you
is
said it-
recommended, I am talking about.
Okay. sir.
Recommended. Here it is also recommended. Recommended. We saw one example like 4-bit
Left
shift
shift.
register or model
Yes,
using
yes.
what? Blocking.
Okay, sir.
Blocking also we have done. But it is recommended that use the non-blocking whenever you are synchronizing with the clocks. Okay. Recommended to use the non-blocking state. See, to model the behavioral mode of style, any good designer, you should know use of this blocking very carefully. Okay, if you are getting any confusion of blocking and non-blocking, the good practice to avoid the confusion is nothing but you write a program, synthesize, you check the output, then you prefer that which one you should use, blocking model or non-blocking according to your design perspective. So there is no straightforward here. Correct. We saw that blocking also can be used to model the what? Sequential circuits also. Correct. So any confusion, you are not getting any output, then you should do what? Checking the blocking and non-blocking statements. And mixed blocking and non-blocking is not highly recommended to do because interpretation of behavior of the model is not straightforward in that case. So that mixed model is not recommended. Is it clear? The differences between blocking and the non-blocking. So in the next session, we'll start working with the timing controls. After that, so we'll be going with control structures like loops, while loop, for loop, forever, repeat loops. Then we'll go with conditional statements like if statement, if else, and nested if statements. Then we'll go with the multi-branching statements like case X. And using this control statement, now you can model the combinational logic circuit and sequential logic circuit using behavioral model. We'll see that in the upcoming sessions. Okay. So with this, let me stop the session here. So we'll continue in the next session. So now I request all of you to fill the attendance. Fill the attendance, all of you. Online student, you can fill the attendance now.
Sir,
Yeah, hello.
sir, in the examples that you have given, the ring counter and all, so all the counters you have used positive edge clock, like always positive edge clock. So
Right.
whenever programming it, I have to design a clock first and then start running the program, sir.
You're talking about in the test bench how to generate the clock. And
No. So
I'm not getting your
this
question properly.
this program when I'm writing in this GVM, here itself I have to
Okay.
first make a clock, then write, like I have to include an always statement with for our clock and then run the write this code, or I write it separately in one more test bench. That's it.
No, whatever here I'm talking about, all these are design files.
Okay.
The design file. Okay. For design file, you write it. These are the design file you write. And then for design file, you can run the test bench. Test bench
Okay.
and simulate and see that whether it is happening at the 4-bit shift register.
Okay, sir.
So I was saying that all these examples, for these examples, you write the design file as well as a test bench, and then you simulate and check the output. What is the difference between the blocking model, how blocking model will be yours, how non-blocking model will be yours. Yes, hello.
Okay, sir.
Okay, let me stop here and we'll continue in the next session.